Hello everyone, my name is Nguyễn Long.
And my name is Nguyễn Hoàng Anh.
Today we will represent our research about recoveries of silicon from decommissioned solar panels for proposing as a raw material in lithium-ion batteries.
Nowadays, in both globally and in Vietnam, we are witnessing the widespread adoption of solar panels as a green energy source. Solar panels typically last approximately 20 to 25 years. At the end of their life cycle, they are collected for recycling to utilize valuable materials, especially silicon. However, recycling silicon for reuse in new solar cells is highly complex, requiring large amounts of toxic chemicals to restore impurities and to restore the crystal structure. Meanwhile, silicon can be used as an anode for lithium-ion batteries, which theoretical capacity of up to 4,200 mAh per gram, which is 10 times as high as that of conventional graphite anodes. For this application, silicon does not require high crystallinity and even benefit from the remaining impurities. As a result, the cost for the purification process, which is accounting for up to 70% of total processing costs, can be significantly reduced. Drawing from this practical background, our group has chosen the topic research on the recovery of silicon from decommissioned solar panels for repurposing as anode material in lithium-ion batteries. The main focus of this project is to exploit the potential of silicon as a high-performance anode materials.
Despite high capacity, silicon suffers from severe volume expansion during dissociation, which leads to structural collapse and rapid capacity fading. To address this issue, graphene, a low-dimensional material with superior electrical conductivity and excellent mechanical properties, was introduced to enhance the electric durability. From this perspective, the project aims to address two main research questions. First, can the silicon be recovered and refined from the waste solar panel using a simple, low-cost, and environmentally friendly process for use as a lithium-ion battery anodes? Second, can the electrochemical performance of the silicon be effectively improved by forming a composite material with graphene? To answer these two questions, there are four specific research objectives were defined. First, to develop a simple project to refining silicon recovered from waste solar panels. Second, to investigate the electrochemical properties of refined silicon and evaluate its feasibility for lithium-ion batteries. Third, to fabricate a silicon graphene composite to enhance electrochemical performance. And fourth, to assemble a prototype lithium-ion batteries from silicon graphene anode and the commercial LFP cathode materials.
Based on these objectives, the research process of the team is as follows. First, silicon was recovered from an end-life solar panels with a physical separation process in section 2.1, followed by a refinement process using acid and alkene solutions enhanced with sonication. The silicon samples before and after refinement was analyzed and compared using ELIX, XRD, and SEM techniques. To improve the electrochemical properties, silicon graphene composite was synthesized by high energy ball mining. Electrodes and half cells were fabricated following the standard process in section 2.3. The electrochemical properties were analyzed using CD when the specific capacity and the life cycle were analyzed using GCD.
The chemical composition of silicon before and after refinement were analyzed by idiots. The results showed that aluminum, which was the main impurity of silicon, was being effectively removed and leaving primarily silicon and oxygen. The study analysis indicates that the purified silicon exhibit an amorphous structure. SEM images reveal that the particle morphology remains nearly unchanged after refinement, with particle size ranging from approximately 5 to 15 micrometers. The electrochemical performance results represent the core finding of this study. The CV curves of raw silicon in silicon electrodes in figure 3.8 display distinct cathodic and anodic peaks, which are corresponding to reversible lithiation and delithiation processes, and demonstrating the rechargeability of the anode material. From the G3D result in figure 3.9, the initial capacity of silicon reaches approximately 1,600 mAh per gram. However, rapid capacity fading occurs and the electrode fails after about 50 cycles. This indicates that recovered silicon can be used as the lithium-ion battery anodes. However, its cycling stability still remains limited.
To overcome the limitation, the silicon graphene composite was evaluated. CV measurements show the oxidation and reduction peaks similar to those of silicon. The composite has a specific capacity of around 600 mAh per gram and can show a stable performance over 100 cycles, demonstrating a significant improvement in the stability compared to the silicon. Subsequently, a full cell was assembled using this composite anode and LFP cathode. Charging and discharging at 0.5 C show the stable performance over 50 cycles. The battery was also can power common LED, highlighting its practical application potential. In summary, this study successfully achieved its objectives. First, successfully develop a simple and effective process to recover and refine silicon from end-of-life solar panels, achieving cost saving at least 50%. Second, evaluated the electrochemicals of silicon after refinement. Third, a silicon graphene composite anode was evaluated, successfully fabricated, and showing significant improvement in stability. And finally, a prototype lithium-ion battery using the silicon graphene anode and LFP cathode was assembled, demonstrating a strong potential for practical application.
Based on these results, several future directions are proposed. First, to optimization the silicon to graphene in ratio in the composite system. Second, to investigation of alternative electrode protection strategies such as the core shell structures or polymer coating layers to further enhance electrode durability. And finally, simultaneous optimization of economic efficiency and environmental performance throughout the recovery and battery fabrication process.